All right. So today is the quiz review. All right, and Wednesday there is gonna be in-class quiz, and yeah, for those who didn't come, please, if you encounter anybody who is taking the class, please make sure they know it's gonna be like an in-class quiz on Wednesday. All right. So what I'm gonna do today is to give you several additional problems to walk through them and kind of to tell you a little bit more about what the quiz is going to be about. So the problems I'm going to cover today in combination with the like self-exercise problems I posted I think 2 weeks ago, and combined with the homework problems you already solved. Those are probably the best review materials you have for the quiz. All right. So what's going to be covered in the quiz? Second, is pretty much the entire module 1 and 2. So first of all, we went through the fundamentals of aerodynamics, and one of the most important thing is using Bernoulli's principle, right? So we went through this incompressibility, basically how to when to use Bernoulli's principle, and computing the pressure out of a velocity field, and also integrating them to compute forces and moments are one of the things we may test in quiz 1. And also another important part of what we're going to be covering is a flow around the airplanes and the lifting line, right? So being able to compute the flow field induced by vortices and adding them up using the principle of superposition. It's a big part of the quiz. And finally, the flow over airfoils and thin airfoil theory. So compared to what I showed last time, there is just the addition of not just how airfoil shapes and angle of attack changes pressure distribution, but also lift and moment and the center of lift, and how the shifting of the center of lift as a result of a changing angle of attack affects stability, right? So these are the things that's going to be covered. So today I'm going to work through one example for each, and in the quiz we are not going to be able to test all 3 problems because each problem might be pretty long, right? So so what you're going to see today is going to be a lot more than what's actually going to be in the quiz, but today I'm going to be working through 3 examples, right? All of them are possible to appear in the quiz. Okay, so first of all, we have the single vortex model of a wing. So the problem is that a very simple model of the flow field around the lifting airfoil is the free stream speed of u infinity aligned in the x-axis. So the free stream is going in the positive x-axis, plus a single vortex of circulation gamma in the clockwise direction. Actually, I wouldn't say in the clockwise direction, just a vortex of circulation gamma centered at the quarter chord of the airfoil, right? Assume that the airfoil is in the xz plane and the quarter chord is actually located at the origin, and we enforce the cut condition so that at the trailing edge of the airfoil, okay, there is no flow in the direction orthogonal to the chord of length c. Yes?
Usually seen it stated as like the flow has to be parallel, like there's only x hat component to the flow.
That's right.
The trailing.
Yeah.
I've also seen it written as the vorticity being 0 at the trailing edge.
Yeah.
Those are the same thing.
Yeah, those are depend on the level of modeling fidelity. They are similar things, but not exactly the same thing. Right, so here I'm using a low fidelity model to model the flow field, right? So there is not even any vorticity at the trailing edge. So as a result, what I can enforce is that the direction of the flow is aligned with the airfoil, right? So there is no flow in the orthogonal direction. But in the higher fidelity model, if I have vorticity distribution around the entire airfoil, right, then I can enforce that the vorticity at the trailing edge needs to be 0, because otherwise the vorticity exactly at the trailing edge is going to be inducing a very large velocity in the direction orthogonal to the airfoil. Yeah. Okay. Right, so in this case, we just use a single vortex model, right? And basically, the first question is, when the airfoil is at an angle of attack of alpha, what is going to be the circulation of the vortex in order to enforce the cutter condition? So basically, this is saying that, okay, we know the quarter chord is at the origin, right? So this is the origin, and the chord is of length c. So there is a quarter c ahead of the origin, and 3/4 c downstream of the origin, and the entire thing is at an angle of attack of alpha, right? And the free stream we know is u infinity in this direction. So if you don't have any vortex sitting at the quarter chord, the velocity at the trailing edge is just the u infinity, and it does have a component, right? Unless the angle of attack is 0, then the free stream is going to have a component orthogonal to the airfoil itself, right? And how big is the velocity component if we decompose the u infinity into the direction aligned with the airfoil and orthogonal to the airfoil? What is the orthogonal component? Okay, the angle of attack is alpha. Yes?
So times sine alpha?
Yes, this component is going to be u infinity times sine of alpha. That's right. All right. Now we add the vortex to exactly cancel that component, right? So that vortex, of course, we know has to be in this direction so that the velocity induced from the vortex is going to be exactly canceling, right? And then what is the velocity induced by the vortex at the trailing edge point? Anybody remember the formula here? That's part of the exam, right? So the formula is actually different in 2 dimensions and 3 dimensions. This is actually the simple version in 2 dimensions, right? It's gamma over 2 pi, right? In 3 dimensions would be gamma over 4 pi. And but there also has to be different sine angles you have to take into consideration. But in 2D, there is no sine angles. It's just gamma over 2 pi, and then divided by the length, the distance between the point and the center of the vortex. In this case, what is the length? Yeah, 3c over 4, exactly. So this is how much velocity is induced, and what is the direction of the induced velocity? Well, it is exactly going circular, right, around the center. So in this case, it is exactly in the opposite direction of the u infinity times sine alpha. So this velocity has to be exactly equal to that. All right, that helps you calculate what is gamma, and it is going to be in the clockwise direction, right? So gamma is going to be, the answer is gamma is equal to pi cancels out, so 3c over 2 times pi times u infinity times sine alpha, right? Okay, any questions? Yeah.
A little bit more related to the exam. Can we use notes?
Yes, yes, you can use notes, and yeah, any notes you can bring, not limited to any pages or anything. Yeah.
Thank you.
Yeah, but no computers, no cell phones. Yeah.
Okay. Can we have the notes in our tablets and the iPads?
No, I prefer you print them. Yeah. Okay. So second question is what is the pressure field, right? Now the pressure field has to be computed using Bernoulli's, right? Okay. And for you to be able to use Bernoulli's, you have to compute the velocity field, right? Okay, we know that we can use Bernoulli's because the flow field is the addition of a uniform flow plus a vortex flow, right? Both are irrotational. If you compute the vorticity out of a uniform flow, is 0. If you compute the vorticity out of a flow field induced by a vortex, it is also 0 vorticity, right? So as a result, we can use Bernoulli. And to use Bernoulli, we want to first compute the velocity field. And that's actually exactly a part of the question I have in the in the practice questions, right? I mean, if you look at that, it's actually it's overlapping. So the velocity field that has an x and y component. So let's just denote as ux is going to be, first of all, we have u infinity, right? And then plus what's induced by the vortex is going to be gamma divided. I ask you to compute the p as a function of x and z, right? So it is effectively gamma over 2 pi r, but because we asked x and z, so the magnitude is going to be 2 pi divided by square root of x squared plus z squared, right? And then there is an angle. There is an angle of the flow. So if you decompose the flow in the x and z directions, you get to divide by another square root of x squared plus z squared. So you have it over here, and in the x direction, it'll be minus z. Actually, yeah, it'll be plus z. So the higher the z is, the faster. When z is higher than the center of the vortex, the induced flow in the x direction is positive, right? And uz is equal to, there is no free stream component, and the induced flow is going to be negative when x is positive. So it's going to be 2 pi x squared plus z squared. Any questions on these formulas? Why did I arrive at these velocity fields? All right. So there is a 1 over square root component, and the decomposition in the two different directions has another z over square root of x squared plus z squared, and also x over square root of x squared plus z squared. Right. All right. Okay. And then with the velocity computed, we can compute the pressure field using Bernoulli's. Okay. So the P, basically P naught at the free stream plus half of rho u infinity squared. That's the stagnation pressure at the free stream is equal to P of xy, xz plus this, right? Plus half of rho times ux squared plus uz squared, right? So that's Bernoulli's, and we already figured out the formula for ux and uz, right? So then we can just compute the p of x and z would be equal to p naught plus half of rho of u infinity squared minus this thing squared and minus this thing squared, right? And if you do the math, the ux squared would be u infinity squared minus 2u infinity times gamma z 2 pi x squared plus z squared, right? And minus another minus another gamma z over 2 pi x squared plus z squared squared, right? And then minus uz squared would be minus gamma x over 2 pi x squared plus z squared, right? Squared. So that would be the pressure field. And for these two components, you can actually add them together, because there is everything else is the same except for there is a z squared and there is a x squared, right? That actually cancels with one of these. And basically you can simplify this a little bit. Yes?
I can't read the last term in that top line. It's rho over what?
Rho over 2, sorry, rho over 2. Yeah, so that's half of rho. Half of rho u squared is the is the velocity component of the stagnation pressure. Yes?
I had a question about the first part.
Yep.
So why is it like part of the Kelvin condition that not only the flow at the trailing edge of the airfoil is tangent to the surface, but also that it has a magnitude of u infinity? Like, why can we say that it's equal to u infinity sine alpha and not some other u sine alpha that was like due to the pressure difference or something like that?
Can you say again, like not only is the flow tangential, but also what?
The magnitude is equal to u infinity.
The magnitude actually doesn't have to equal to u infinity. So so for airfoils, like, yeah, the magnitude actually doesn't have to be U infinity. For airfoil with a finite angle at the trailing edge, the flow is not equal to U infinity at the trailing edge.
So how can you say that the normal component, like what allows you to say the normal component is U infinity times sine alpha, versus just some like arbitrary U times sine alpha?
Oh, so this is because the entire flow field is modeled as a linear superposition of a uniform flow field, which is just U infinity in the x direction and 0 in the y direction. So that's velocity field number 1. Velocity field number 2 is the flow induced by the vortex, right? So the velocity here as a vector is just a summation of these two flow fields, right? And basically one flow field is in this direction, the other flow is in this direction, and the color condition here explicitly says that we are enforcing that the summation of these two flow field is in the direction parallel to the airfoil. Right, so that's why like we are basically this is a vector superposition of these two flow fields that leads to this sine alpha. Yeah. Yes.
Could we explain on one the direction of circulation again?
Oh, why is the direction of the circulation?
Yeah.
Yes. So the direction of the circulation is such that the red velocity is the velocity induced by the vortex, right? The black velocity is the first component, the free stream component. Basically, the summation of them has to be tangential to this direction. So I basically change my coordinate so that we are analyzing a coordinate that is along the airfoil and orthogonal to the airfoil. And I'm just adding along the airfoil, it doesn't matter, right? Because it's not part of the condition. And orthogonal to the airfoil, I have two velocity components. One is the free stream, which is U infinity sine alpha. The other one is induced by the vortex, which has to go against the velocity from the black component, right? So that makes sure that the circulation has to be in the clockwise direction. Yeah, so that induces this red velocity. All right. Okay, other questions before I go on to integrating the pressure? All right, so now the next question is basically integrating the pressure, right, to get the total pressure force per unit span on the control volume. So here I'm drawing a control volume of radius r, right? And essentially what I need to do is to integrate this pressure field multiplied by a unit normal on this control volume. So the unit normal is going to be having a direction of x over square root of x squared plus z squared and z over squared plus z squared. So that's my unit normal of the control volume, right? Okay, so if you so that's my n. So if you multiply p with n, okay, first of all you can do some simplification on p, right? As I said, so the u infinity part cancels out, all right, and this part becomes minus 2u infinity gamma z over 2 pi x squared plus z squared, and the third part, as I said, the z squared plus x squares they combine to cancel with part of this x squared plus z squared. So it's only, so what I want to say is it's just a function of r, right? Okay, so basically if you add x squared plus z squared, it's r squared, right? And everything else in this equation depends on x and z only as a function of x squared plus z squared. So it's just a function of r. And we are going to see that when we integrate just the function of r over this circle multiplied with a unit normal, it'll just go away, right? Because we are basically integrating a constant multiplied with a unit normal. Okay, so so basically we are going to be integrating over this this, let's say, surface p times n. Okay, and First of all, the P0 term cancels out because we are integrating over closed contour, right? And we are multiplied with a unit normal. So any constant multiplied with a unit normal integrating over a closed surface, it goes to 0, right? And also this one is essentially a constant because it's a function of r, and over this surface we have constant r. So both terms goes away. The only thing we have is this minus 2 and 2 cancels, rho u infinity gamma z over 2 pi x squared plus z squared times the surface, right? ds. Okay, and basically, and also times the normal. All right, okay, and so something you can further transform is that okay. So let's express this angle. So let's use an angle theta. And if we use the angle theta, this unit normal is actually going to be cosine theta, sine theta, right? That's the unit normal. And the x squared plus z squared is actually what? What is x squared plus z squared? We have a radius r, right? That'll be r squared. And also z over square root of x squared plus z squared. Actually, let me write it out. So we have 2 pi r squared, but like one of the r can be combined with the z to form a sine theta, right? Sine theta, and then times my cosine theta, sine theta, and the ds can be written as r times d theta times the span, right? Times the span can be written out. And so because I'm calculating the force per unit span, so let's just assume the span is equal to 1. So we are going to be basically having an integral of either sine theta times cosine theta or sine theta squared, right? So what is the integral of sine theta times cosine theta over a circle? Well, I mean, you can think about it several ways. One way is, if you remember, sine theta times cosine theta is equal to half of sine 2 theta, right? And the sine 2 theta integrated over a circle is equal to 0, right? So the first part is equal to 0. The second part is sine square theta. What is integral of sine square theta? Not 0 anymore, right? It's an integral of a square, right? Integrating something that's positive. Well, if you remember the trigonometric relationships, sine square theta is equal to half of 1 minus 1 minus, right? 1 minus cosine 2 theta, right? The cosine 2 theta part integrates to 0, and only the half part actually integrates to a non-zero. So anyway, so the first component is 0 because we have sine theta, cosine theta. The second component is minus this gamma, and okay, so this is from 0 to 2 pi, right? And the second part is we have r 2 pi, and we have another r. The r actually cancels out. And integrating a sine theta squared actually gets to half times the length of the integral, so that's actually pi, right? Okay, so that's 0 minus rho u infinity gamma over 2. So that's the pressure integral. All right. Okay. Any questions? The integral might be a little bit yes.
Yeah, there's flow across the airfoil. Are we assuming that, or like I'm kind of confused about the assumptions. So we enforce the color condition at the trailing edge, but
yeah,
not necessarily at the whole airfoil.
Yeah, not at the whole airfoil,
Okay.
right? So as I said, this is a very simple model of the flow around an airfoil. It is not a good model of the flow through the airfoil,
Okay.
right?
Yeah.
Okay, yeah. You have a question?
There's typically a negative sign when you wrong.
Oh, why is there a negative sign? Yes, because I'm computing the integral of pressure times the unit outward normal. What does that mean? That means I'm computing the force exerted by the control volume to the outside of the control volume, right? So the actual answer of what is the pressure force on this control volume should be the negative of what I computed over here, right? So what I need to, actually the answer should be integral of P times negative of this outward normal, right, ds, which should be 0 and a positive rho u infinity gamma over 2. Yeah, thank you for pointing that out. So that should be the correct answer. All right. Okay. Any more questions? Number 4 is the total momentum flux into the control volume turns out to be the same as the total pressure force, right? I mean, in the practice question, there is also an answer that actually calculates the total momentum flux, but here it doesn't require you to do so. Basically, it asks you to do the momentum conservation, right? So if the pressure force is this and the momentum flux is also this, right? Then you can just use a conservation of momentum to figure out the lift per unit span actually has to be basically double of this, rho infinity times gamma, not divided by 2, right? So basically that's a derivation of the Kara-Joukowski theorem. All right. Okay. So basically that's basically saying that the force on this, so the flow field is a steady state, right? There is no unsteadiness. So the change of momentum is 0. So that means the total force plus the flux into the volume has to be 0, right? What are the total forces? The total forces are the forces onto this control volume from the nearby flow, plus the force onto the control volume from the airfoil, right? Okay. So if the momentum flux is equal to this, then the total force has to be negative of this, right? And there is also a pressure force equal to this, which means the force from the airfoil has to be downward and equal to this magnitude. That's the force exerted onto the fluid by the airfoil, right? That's equal to that, downward. Which means the force exerted by the fluid on the airfoil is going upward and of this value. All right? Okay, make sense? Yes?
Why do it differ by a factor of 2?
Oh, this is because I said that there is also a momentum flux, right? So let me just write out. The total momentum flux is equal to rho u infinity gamma over 2, right?
Oh, I see.
So that has to be equal to is equal to the previous answer, right? Plus force by airfoil, right? So that means the force by airfoil has to be 1 second. No, plus them, not equal. So the this is the momentum flux plus the force by the outside fluid plus the force by the airfoil has to be equal to 0, right? That's equal to 0. That means the force by the airfoil has to be negative of rho u infinity gamma, right? And which means the force on the airfoil is going to be positive rho u infinity gamma. Okay. Okay. So finally, it asks you to plug in this gamma, right? And the lift is going to be, so lift is equal to this. Lift is equal to rho u infinity. Gamma would be this guy, 3 pi over 2 u infinity sine alpha, right? So how does the result differ from thin airfoil theory, right? So thin airfoil theory tells me that L is equal to half of rho u infinity squared times 2 pi alpha, right? And this answer turns out to be, well, if we just pull out a rho infinity square, you can pull out these, and you get actually 3 pi times sine alpha, right? So the sine alpha actually agrees with alpha at small angle of attack, right? Sine alpha is approximately equal to alpha. So if you have alpha, sine alpha, like at small angles, you have a tangent, you have a tangent line. So this and this actually agrees, but the 3 pi does not agree with 2 pi, right? And if you want this to actually agree, instead of enforcing on the trailing edge, you should actually enforce the cutter condition at 3/4 of the chord, so that this length is actually half of C. If you actually make this half of C, you can figure out that the result is going to agree with thin airfoil theory. All right. Yes?
How would you calculate that total momentum flux for, like, I mean, I know it's there on the problem, but how would the total momentum flux be that?
Yeah, so you calculate the total momentum flux by actually doing another integral, which is very similar to this. So the other integral, the total momentum flux would be an integral of the velocity dot with n, right? Basically the velocity in the normal direction times velocity, and calculated using ds. And you have to plug in velocity, plug in n, and do another integral also using trigonometric relations. So it turns out to be the same. Yes.
Would there be any reason that you want to make the thin airfoil theory consistent with that you would want to do the cutter condition at 3C/4 versus the trailing edge, or is that just to show the error?
So there is motivation because this model, right? If we want to use this model is a lower fidelity model than thin airfoil theory, right? So it does make sense to have some kind of an empirical adjustment to this theory so that it fits a higher fidelity model like thin airfoil theory. Yeah. Okay. But that's actually a lot of lifting line theory code enforces the cutter condition at 3/4 of the chord. Okay, let's actually. I might not have time to go through the entirety of the two other problems, but first of all, let's consider a single vortex on a swept wing, right? And I'm calculating the induced velocity at the center of the left half of the wing. So this is really a test of using the formula of induced flow, right? The induced flow, especially, let me just write it down. Okay, so first of all, because we are, all these vortices lies on the same xy plane, right? So the only induced velocity at the point A, which is also on the same plane, is in the z direction, right? So let's just write not a vector. Let's just write the scalar w. And if you look at this point, the point is already on this vortex, so it has no influence from itself. But it does have influence from, let's say, 1, 2, and 3, right? So basically, the question asks you to add up the influence from all the 3 vortices. And all of them has a, let's see, first of all, let's figure out the sign, right? All of them have, if you use the right-hand rule, induces a downward velocity over there. So let's just put a negative sign in the beginning. So gamma over 4 pi is the constant that's common among everything. And then from term number 1, we have 1 over, first of all, the distance, right? What is the distance from here to here? So we know that this the span is equal to b. So the distance here, actually the length of this is b over square root of 2. So the half of the length, right? Because of the 45 degrees, this is a right angle. So we have this distance is b over 2 times square root of 2. right? Okay, and we also need the difference between the sine angles. So we have a 0 over here, right? So because it's a right angle, but there is a non-zero sine angle over here. So it's sine of this angle. We get we get what is it? So yeah, if we do the math, this is a factor of if this is a, this is 2a, right? And this is square root of 5a. So basically the sine angle would be 2 over square root of 5 minus 0. So that's the from the first vortex. Okay, so let's look at the second and the third vortex. From the second vortex, we have a infinitely large angle from here, right? Okay, so let's first figure out the distance. The distance of this point to this vortex is 3/4 b, right? I mean, so this is 3/4 b, and we are going to do this vortex last. It's 1/4 b, and the angles are 1 minus. You need to figure out the sine of this angle, and because this is 3, this is 1, and it turns out to be 1 over square root of 10. Okay, and finally you have the last part over here, and it's 1 over 1/4 b, and 1 minus the sine angle is 1 over square root of 2, right? So that's basically the summation of these three contributions from the three vortices. It's basically an exercise using the formula. Yes?
What is the angle that says b over root 2? What does that say right there? Like
What color is it?
red. That's
Here?
No, up. The angle in between.
Oh, here. Oh, no. It's just the same. The distance between A and the first vortex is b over 2 times square root of 2. Let me write it more clearly. 2 times square root of 2, right? Yeah. This leg has a length of b over square root of 2, so the distance between this and this is b over 2 times square root of 2. Yes?
Can you say one more time how you got like the 1 minus 1 over square root 10?
Oh, okay. So 1 is from the angle, right? The sine of the angle between the distance to this vortex and the infinite end of the vortex. So it's a sine of 90 degrees, right? So I mean the 1 is there when a vortex goes to infinity, right? So for example, if you have a double infinite vortex, you will get 1 minus 1. So you get a factor of 2, which cancels the 4 in the 4 pi and makes it 2 pi, right? That's why like a 2-dimensional vortex has gamma over 2 pi. So the 1 is from like the infinite direction, and the 1 over square root of 10 is the sine angle of it's the sine of this angle, right? It's sine of this angle. For this angle, you get a factor of 1/3 for this triangle. So the hypotenuse would be square root of 10.
Okay.
Right, so it's 1 over square root of 10 as the sine angle. Yeah, we're kind of this is kind of the easiest to calculate case for a swept wing, right? The 45-degree case. Otherwise, you get all kinds of different angles. All right. Yes.
Just to clarify, we're saying that root 5a is the same as square root of 10. It's the same hypotenuse, right?
Little, I think.
Yeah. Root 5.
Oh yeah. That's right. The root 5a. Yeah. So yes. So basically, if this is a, this would be a over square root of 2, right? So basically, you get two different triangles. This triangle has a it's a little bit thinner than this triangle, right? And this is actually a square root of 2 smaller than this.
Okay, so you're saying the hypotenuse that they share, that
Yeah.
has to be the same length, right?
Yeah, the hypotenuse they show is the same length, square root of 5 times a, but this side is different, right?
I mean, yeah, one's thinner and taller, one's.
Yeah. Yeah. All right. Yes.
As far as angle is concerned, it's that angle would be like upper right of that triangle, but like the one that's having the sign taken.
Yeah. So we are always so the angle we are looking at is the angle between the connecting the line between the point and the end of the vortex versus the line that is the shortest distance to the line on which the vortex lies. Right. So for example, for number 2 vortex, we would be looking at we take one end and connect it to A. So that's one line. Another line is look at what is the shortest distance to the line that defines the vortex, and it's the sine of this angle. And then just in this case, it happens this angle is the same as this angle, right? So we use that. Right. Okay. Okay. So that's the induced velocity, and assume the wing is flying at a speed of u infinity in the negative x direction, right? So which means the free stream is in the positive x direction, and the airfoil is at alpha degree angle of attack. So basically, it asks you to take u infinity, right? U infinity, and add this w, which is negative, and yeah, it essentially looks at how is this angle changing the effective angle of attack. So alpha effective is equal to alpha minus arc sine of arctangent of well, it's actually plus because the w is negative, w over u infinity, right? So that's going to be the effective angle of attack. And finally, it asks you to describe, you don't have to solve it, but essentially describe how the circulation gamma can be related to this effective angle of attack, the chord length, and the free stream velocity. So, and so this, combining this equation with the equation for w is going to get you a closed form that you can solve for this this gamma, right? So if the gamma, we can basically use the thin airfoil theory to predict the lift coefficient, right? And therefore to predict how much lift there is. And we can also use a Kudai-Joukowski theorem to relate that lift you compute from thin airfoil theory to how much circulation you have, how much gamma you have. So that gives you an equation that you can solve for gamma. So basically, it asks you to describe this. I mean, it's describing a procedure that you went through in your homework, right? All right. Okay. So let me go to the last problem. So the last problem is basically like thin airfoil theory and stability. It asks you to consider an airplane with 2 wings, a main wing and a horizontal tail. Okay, and both have the same chord length. And to make the problem simple, we are also saying both of them have the same span, which is not very realistic, but like it makes the calculation a little bit easier. And also the span is much larger than the chord, so that you don't have to consider any 3-dimensional effects. So it's just a 2-dimensional problem. And the distance between the trailing edge of the wing and leading edge of the horizontal tail is 2 times the chord length. So first question is at 0 degrees angle of attack, what is the lift per unit span, right? So basically you just read the lift coefficient and moment coefficients from here, right? So basically the horizontal tail contributes nothing in this case. Okay. And the aerodynamic moment per span, it's basically testing the definition of the lift coefficients and the moment coefficients. You just multiply them with half of rho u infinity squares times c, or c squared if it's the moment. All right. Okay. And what is the center of lift? That basically tests the formula for the center of the lift. Because of the horizontal tail doesn't contribute anything, you can just have xc is equal to basically quarter chord. Let's say this is x equal to 0, right? Then it is equal to quarter chord times the chord times cm over cl, right? And both are actually reported over here. Okay. Now, the real meat of the question starts with using thin airfoil theory. How does the lift and moments change, right, for both of them at 1 degree angle of attack? You have a question?
Yeah. After or if the front wing generates a generous lift pushes air downwards, that means that the horizontal tail is an effective angle of attack. Are we not considering that?
Right. So we are not considering that because we are saying, okay, we are saying the span is much longer than the chord, right?
No, but I mean like only considering to the effects, it will still be at an effective angle of attack if the air is moving downwards at the trailing edge of the front wing, right?
Yeah, that's right, and that's a good question. So yeah, I actually should also say that we should neglect the effect, the downwash from the front wing on the rear wing. So, but that's a very good point. In reality, there is actually there is also a downwash that comes from two-dimensional effects. Yeah, that's a good point. Okay, so yeah, if I have this in the quiz, I should also say that ask you to neglect the downwash effect. Yeah, thanks. Okay. Yeah. Let's see. Downwash from the other surface. Okay. Right. Now, basically, in thin airfoil theory, the moment coefficient does not change, right? And the lift coefficient goes up by 2 pi times 1 degree converted to radian, right? Do make sure you convert the 1 degree to radian before you multiply by 2 pi. So that's how the lift coefficients are going to change. Now, at 1 degree, what is the total lift per span and the total aerodynamic moment around the quarter chord of the wing? So here, this is more of a tricky question because I had a note over here. The moment coefficient of the horizontal tail is defined at its own quarter chord, not the quarter chord of the wing, right? So, but here I'm asking the total moment around the quarter chord of the front wing. So basically you have to consider, okay, so we get a moment from the front wing itself, right? On the hind wing, there is a lift and there is no moment around its own quarter chord. But this lift, which you can calculate from the 1 degree times 2 pi, right, this lift does have a moment around the quarter chord of the front wing. And the moment lag is actually 3c, right? So basically, not only you have to consider the moment from the front wing, you also have to add the moment from the horizontal stabilizer. All right, with basically multiplying the lift of the horizontal stabilizer by a moment arm of 3c, right? Is it clear why we have to add that component? Okay, all right, and right. Finally, it asks you to recalculate the center of lift at 1 degree angle of attack using the new moment and the basically new total moment and the new total lift, right? And compare with this center of lift and figure out, okay, is this system stable or not stable? All right, is it clear? I don't have time to work through this with numbers, but is it clear what? Yes.
Yeah, pretty clear overall. I guess my one question would be, when you get the moment coefficients, again, do you still renormalize like with respect to all one chord length? I guess.
Yes. Yeah. It asks you the lift and moment coefficient of the wing and the horizontal tail individually, right? And in problem 4, then we combine them together, right? In problem 4, we are no longer asking for coefficients, but the total moment and the lift. Yeah.
I would just ask, would it be possible that you could work this out and post it so we could review it before the exam?
Okay, sure. Yeah. Okay. Yeah. Yeah, I'll do that. Other questions? Okay, so I'm gonna be having an office hour downstairs. You can keep asking any questions. All right, cool.